Good afternoon, everybody. Welcome to our seminar. It's my great honor to introduce our speaker, Dr. Ed Zipser, today. And I think there's no doubt that Ed is there is no doubt Ed is the most productive, most famous, most accomplished, and most honored member of our department. And making it somewhat difficult for me to introduce Ed properly to the seminar. So I nevertheless tried this a little bit, and I asked him to send me a bio of him today. And that goes, and I realized that this goes back to 1958. I mean, I was not even born during that time, and I would say most of our faculty members were not born at that time. And Ed already received in 1958 his PS in aeronautical engineering at Princeton University. And well, then he moved on. In 1965, he received his PhD in meteorology at Florida State University. And then he stayed for a very long time at NCAR in various positions. Actually, from 66 to 9 is essentially 25 years, if I count this correctly. Yeah. And then he moved on in 1990 to become professor at Texas A&M for exactly 10 years. And he was also head of the department there for 6 years. And since 1999, Ed came to our department. He chaired the department from 1999 to 2005. And I remember, like, I was hired under Ed's chairmanship. Shausha was hired, and I think also Kevin and Tim Garrett. So 4 faculty members were hired by him, yeah.
There's some things I can be proud of.
Yeah, of course. No, it's just interesting, you know. And that's already a long time ago, right? Yeah, so I mean, Ed is still with us, fortunately, and very productive. And so Ed's research in general is concerned with mesoscale storm system, understanding those systems using satellite information, satellite data. And he did this by realizing and carrying out important, actually a large number of NASA field programs. Ed also received many important honors, and there are too many to list them all separately, but I selected the 2 most important ones, which I think are: he became fellow of the HEU in 2017, and he received the AMS Carl Gustav Rossby Research Medal in 2016. And yeah, maybe also to give you some impression, Ed authored so far at least 145 scientific publications. And with that, I would like to hand over to Ed and ask him to give his talk.
Okay. Can you see the screen?
Very good.
Okay, good. Well, thank you, Thomas, and all of my wonderful colleagues for putting up with me for so long. And I've had a lot of fun doing this work over the years, and looking forward to some more. There's field campaign number 40 is scheduled for this summer. So let's hope everything goes well. Okay, I think the title slide's on long enough. Let me put the talk outline on here. On my screen, the right-hand side is cut off. Is it cut off for you too? No, I think it's probably all right.
No, it's fine.
Okay, great. Okay. Well, I want to start by giving credit to at least 30 years of work by my current and former students, including all those people that I have listed. The last 15 or so you will all recognize as being students here at Utah. And I'll say a few things later about my long-term colleague, Chantal Liu. But some of you will recognize, may remember Dave Yorty. Dave Yorty, when he was a master's student here in our group, found out about the satellite data that we had and decided that he was interested in using it to determine where the strongest storms on this planet are. And I said, well, that's an interesting project. Well, he got a master's thesis out of it, but we didn't finish writing the paper for quite some years. So, but his name's on it. So at any rate, like many of us, our success as faculty members depends on the quality and productivity of our students, and that's certainly been true for me. I will show a few examples of contrasting extreme events in the West. One of them is the Fort Collins, Colorado flood. The other is a southern Utah disaster. They were both small, intense storms, but they couldn't be more different. And so I'll use those to illustrate two of the differing extreme types of weather events. I will mention our earlier paper on global distribution using TRIM, mention some of the limitations of that paper, and then finish up by showing the global distribution of using the GPM KU band radar so that we can go from 65 north, 65 south. And although I probably won't do it, I will mention a few future directions where this work ought to be expanded a little bit. A big hint to other faculty members. Okay, well, here is the paper that I'll start talking about a little bit. It's actually the one that eventually emerged from Dave Yorty's thesis, but without Chantal and Dan Cecil and Steve Nesbitt, we couldn't have written that. I think it's maybe the title that is responsible for this having the most citations of any paper that I've first author on. People are interested in questions like that. So I just want to spend a minute or two showing the results of the answer to that question using TRIM, which only goes from 35 south to 35 north. You will see that cutting from Central California across to North Carolina. And these three panels are, and the color code goes from least intense to most intense. And since the subject was thunderstorms, the flash rate of those thunderstorms by the LIS instrument on TRIM is part of the data set. And so what you see here is over continental North America and South America and Africa, the flash rate on some of these storms is really extreme, 300 flashes per minute for this color. Notice how well correlated that is with the height reached by the 40 dBz radar echo. And for those of you not familiar with radar meteorology, 40 dBz is a pretty strong radar echo. And if it extends into the stratosphere, you have a really severe, intense storm. And 85 gigahertz passive microwave radiometer is an extremely useful channel because it basically is sensing the radiation received at the satellite that started out at roughly the temperature of the surface, but is attenuated very strongly by ice, so that if the signal starts out at, say, 300 Kelvin from South America, but encounters a very large optical depth of ice at that frequency, the brightness temperature will appear at the satellite sensor as less than 100 Kelvin. What you see over land is a really nice correlation between the amount of ice in the column, the height reached by the very strong radar echo, typically up close to the tropopause, and the lightning flash rate. There's an interesting feature in the tropical oceans. Look here at the tropical Pacific, for example, where there's enough depth of ice to lower the temperature down, let's say, in the range of 100 to 150 Kelvin, but there's not enough strength of convection to bring the 40 dBz echo up high enough or for lightning. So a lot of these storms over the ocean have little or no lightning. And so that's one of the reasons that you see there's plenty of storms with deep ice over the oceans, but typically they're not intense enough for the radar echo to go deep or for lightning. Okay, moving on, I will now talk a little bit about extremely contrasting events as sort of advertised in the abstract of this talk. The Fort Collins flood, some of you may remember this. It's a nice paper by a lot of colleagues, including Dick Johnson, who just had a session in his honor at the annual meeting, and a lot of colleagues from CSU at that time, and maybe some now. That was an extremely intense flash flood without any evidence of intense convection. And whoops. Okay, here is the, I'll just show a couple of images from this paper. That's 10 inches of rain in 6 hours. You don't see that too often in the Rocky Mountain West. And in fact, that 10 inches of rain happens to be right about where my daughter and her family live right now, very close to the Foothills campus, which is right about here. If you look at the sounding over here, you'll see that it is not a severe weather sounding. It is basically a soaking wet, moist adiabatic sounding. And that's one of the reasons that you have very heavy rain. This is radar echoes. Here's the freezing level. And you have intense radar echoes at low levels, very weak radar echoes above the freezing level. And if you look at the profile of radar reflectivity with height, the dark line is the appropriate sounding for the Fort Collins flood, and the other two lines are the typical reflectivity with height profiles over tropical oceans from extensive tropical field campaigns of Gate and Toga Core. In contrast, some of you might remember only in 2015, the storm with the record number of fatalities in the state of Utah was a flash flood storm down in Hillsdale, right near the Arizona border, 20 fatalities. And that was a completely different character of storm. There were actually two cells that both passed over the same area, and the Jim Smith has done the analysis on this, and he has one of the things he does. He doesn't just rely on the radar for the rain data. He relies on the cubic feet per second measurements of the stream flow. And, clearly this was a major event with, and although I don't really have the slides to demonstrate that to you here, we have not 40, not 50, but 60 dBz echoes in this storm. And the storm height goes basically to the tropopause. So this is a classic, small, very severe thunderstorm. And it happened to pass over the wrong place at the wrong time and killed a lot of people. So I'm going to show you some evidence from a previous paper that Chantal and I were involved with our Japanese colleagues, where we attempted to look at the global distribution, at least as far as TRIM would allow us, and look and ask basically the question, does the heaviest rainfall come from the most severe, intense storms? And the answer, as I think you already know, is sometimes yes, but fairly often no. And let me, oops. Yeah, so here, all I want to do is show one slide from that earlier paper by Hamada and et al. In Nature Communications, and basically just look at the contrast between this top row, which happens to be the TRIM echoes over land in the most intense storms. And here you have the radar profile that is fairly similar to what you had in that Fort Collins flood, with very intense echoes, very intense rainfall rates, but very weak echoes above the freezing level, and very weak echoes indeed going up to the tropopause. You contrast that with this type of storm here, where you have intense radar echoes to the tropopause, but not such intense echoes at low levels. Notice this one goes to 55 dBz, which could mean rain rates of the order of 50 or 100 millimeters an hour. Here, assuming this is rain and not hail, much less intense, probably not a flood disaster. And we looked at this over land and ocean. Well, there were two limitations to this study, although it basically tells the truth about global distributions, had a couple of limitations. One of them, of course, is simply that TRIM only goes to 35 north and south. But the other is the methodology that we used basically insisted on counting all the storms, counting every box in the TRIM orbit between 35 north and 35 south, regardless of how strong the storm was in that box. And so in subsequent papers, we were criticized for including large parts of the world where neither type of severe storm actually existed. So when we came to write this current paper, we will try to correct that. And let me move on. Whoops. I'm going to just tell a short story about the big argument that not really a very, it was a friendly argument, but Jim Smith took exception to what a lot of people were saying, that the so-called low echocentroid structure of flash flooding, people had talked about ever since the Big Thompson flood catastrophe, the Rapid City storm, the Rapidan storm, and the Fort Collins storm. And so a lot of people were asking the question, well, you don't really need very severe thunderstorms for a flood disaster. You can have them with these so-called low echocentroid storms that don't have any strong echoes getting anywhere near the tropopause. And so Jim kept teasing me about this for quite some time. This is one of his classic papers about a storm which is not terribly severe, but caused a lot of damage. But here's the paper he wrote that basically said, take that, Ed. Here's a supercell thunderstorm over Dallas, Texas, with tornadoes and hail, and it had 16 flash flooding deaths. So don't tell me, Ed, that that flash floods are from non-severe storms. They can be, but just as often they are from really severe storms. Okay. And then many of you may be aware of this paper by Eric Nielsen and company, including Russ Schumacher from Florida State. There are storms where tornadoes and flash floods are threatening the same place at the same time. And that's, of course, one of the things Jim Smith is talking about. But these are so-called TORF events, or tornadoes and flash floods, from the same convective cell. And I remember back when I was in Boulder, there was a well-known storm that hit Cheyenne, Wyoming. It killed a woman who took refuge from the tornado warning in her basement. There was a flash flood carrying hail down the street. The flood and hail broke her basement window. The house filled up with water and the poor woman drowned. Something similar happened in Austin, Texas in the 90s with more than one person killed who was taking shelter in basements from the tornado warning. So the National Weather Service has been very much aware of this type of dangerous storm for some time. But so at any rate, this says Jim Smith won the debate. There are a lot of those types of storms. And now I think with that as the background, Chantal and I decided, well, it's time to write a paper that uses the quantitative radar data to define the difference between these very different types of destructive storms. And so the remaining talk here will outline some of that recent paper, which is this paper here. In many ways, it's the strangest experience that I've ever had writing a paper. I was invited by the editors of Current Climate Change Reviews to write this paper. And I said, okay, I'll do it. Of course, I knew I needed Chantal's help. What was strange about it is that after waiting months for the reviews, I get an email from the editor that says, your paper's been accepted. I never saw a review. So to this day, I do not know whether the editors liked it and accepted the paper without review, or maybe they got reviews that they didn't pass on. I have no idea why it was accepted, and I never saw a review. I just have to hope that the editors actually read it. So anyway, that was 2 months ago, more than 2 months ago, and on less than a week ago, I got an email from this publication that said, hey, congratulations, you're now in print, and sent me a link to the paper. So I was waiting about two and a half months for that. Okay. What we needed to do to write this paper was to, what we decided that we should do to write the paper was we knew how to define events. So just like that Hamada et al. Paper, we wanted to define a type of event, something like that Fort Collins event, where there's extremely heavy rain rates. And how did we define that? Near surface reflectivity of at least 50 dBz. Now, you know, we could spend days in a course on radar meteorology explaining that there's a lot of different ZR relationships. There's a lot of issues you have to worry about when you are translating near surface reflectivity into a rain rate. But unless hail is contaminating the radar echo near the surface, trust me, 50 dBz is a very heavy, is a very heavy rain rate, at least 50, maybe 100 millimeters an hour. And so for this so-called R only, where we are trying to rule out the possibility of a severe storm, we insist that the 40 dBz echo not exceed 5 kilometers above the surface. That's a pretty extreme, shallow, heavy rain event. I'm not going to talk too much about H only, but in contrast, the so-called R plus H, in other words, heavy rain with intense echo going very near the tropopause. We also say the maximum near surface dBz is in the 50s, but the 40 dBz echo needs to reach at least 9 kilometers. That means large ice particles are existing so high in the atmosphere that they're existing way up in cold temperatures, and very often that means reaching the tropopause. The so-called H-only event is a peculiar one, where you have a very severe storm which has relatively not so intense rain echoes near the surface. That turns out to be pretty rare, and I'm not going to talk as much about that. Okay, let's look at how this looks. What we had to do, let me go back one. Whoops. So the goal was to map the 1,000 most extreme events. Well, we had to vary we basically decided that we had to vary the size or the rain volume, because if we just use the same rain volume, say here as here, we'd get a very different number than 1,000. So we adjusted the size or rain volume to yield exactly 1,000 events. So what does that mean in terms of area? For the small events, nothing is smaller than 9 pixels of the GPM of 9 pixels of the radar. The footprint size of the radar is about 5 by 5 kilometers, so it's about 25 kilometers square. And we didn't accept anything that was 1 pixel. We accepted only a storm that was 9 pixels, but that's still a pretty darn small storm. That's something like 10 by 20 kilometers. So it can be an individual storm. The median area is not that much bigger over there. So turns out that H-only small, that is intense echoes, an intense storm with relatively moderate rain rates at the surface is pretty rare, and we're not going to talk that much about them. R plus H basically is an intense storm with heavy rain rate. And here, once again, are the 2 examples that sort of give you the graphical image of what they look like. Here we have on the left-hand side, basically just look at the radar echo image here, although the storm height is here. This is basically something resembling a frontal rain band off the coast of Maryland. And it does have significant ice scattering signature, but notice there's very little echo above the freezing level. If the freezing level is, say, 4 or 5 kilometers, basically the echo top is at 8 kilometers, but the rain intensity is, and with this 1 pixel, over 100 millimeters an hour, and very intense low-level echo. So clearly this is rain being formed mostly by collision coalescence near the surface. Contrast that with the image on the right, which is basically a large, intense squall line with trailing stratiform echo behind it over South Dakota. You have 40 dBz echoes exceeding the tropopause, and also very intense echoes near the surface. Some of that may be hail. I'm pretty sure a lot of that's rain. So these 2 are, fairly typical examples of what we call R only and what we call R plus H. So now let's see if we're ready to look at the global distribution. Yep. Okay, let's have a look at the global distribution, 65 south, 65 north, of heavy rain, small echoes, small showers with heavy rain, and I see some surprises here. I expected a lot of this to be over the ocean. Some of it is, but a lot of it's over land, and it's very well distributed over land. What surprised me quite a bit, and you'll see more surprises like this as we go along, is this type of small, where's my cursor here? This type of small, intense rain event. Notice there are a few here in the West. There's a lot of them in the high plain, in the Central Plains and in the East. Some of them around the islands. Very little in the tropics. To me, that's a surprise. Now, if we go and look at large events, remember the one I showed you off of the Maryland coast is sitting right here in the middle of this band. So what are these large, shallow storms with heavy rains? What do they look? Where are they? Mid-latitude oceans. Look at the southern hemisphere. A continuous strip all the way from between roughly 30 and 45 north, circumpolar. What would we call a system like this? If it's approaching the West Coast, you might think of it as an atmospheric river. At least atmospheric rivers might resemble this type of event. Okay, shall we move on? H only, very intense events, very intense convection, not such intense rain race at the surface. Basically land only, and I think some of these may be slightly artificial because being in the mountains, that changes the elevation that we're looking for. But ignoring that, you also notice a pretty big difference between Africa and the Amazon. More about that later. Okay, now let's look at what we might call the classic severe storm. Let's see, how am I doing on time? Not too bad. The classic severe storm. Intense convection, radar echo up near the tropopause. Nothing over the ocean, folks. Nothing. It's all over land, but when we contrast Africa with the Amazon, we start to see why people occasionally call the Amazon the Green Ocean. There's much more intense convection in tropical Africa than there is in tropical South America. The distinction is not quite so great when we look at the medium size and the large size. But basically, there's not really a lot of difference between the small, medium, and large in terms of their geographic distribution. A few of these large guys show up over the ocean, whereas they don't show up, don't show up here. Okay, again, signs of the Green Ocean. The Amazon doesn't have very many of those compared to Africa. Also notice that over the United States and northern Mexico, if you restrict the size to small events, something like the southern Utah example that I've showed, there's quite a few of those in the Intermountain West and the high plains. As you go to larger systems, go here to the really big systems, you now need to go into the plains and into the central US to find that. So you might call this Tornado Alley, and that's that. Okay, moving on. Okay, that's one more, just one more look at these contrasting events. This is the severe storm with heavy rainfall. This is the non-severe storm with heavy rainfall and nothing going very high. Okay, I think we can let's leave a little time for questions by just showing some conclusions. One conclusion, and this came as a bit of a surprise, is when we decided that we had to differentiate the events by size, in addition to type, it made a big difference on their global distribution. So clearly, this is hinting at what meteorological factors are required for those events. And as expected, there are really big differences between events with extreme rainfall rates and with extreme convection. And it's related to their distribution. Small, intense rain events without intense convection are surprisingly well distributed over land and ocean. And some of these are not much bigger than individual convective storms. But there's a big contrast. Once we look for large events like this, they are essentially exclusively oceanic, exclusively mid-latitude. I would guess that many of those we would call atmospheric rivers, and clearly they're forced by large-scale baroclinic waves or frontal systems. And it came as a bit of a surprise to us that a lot of these most largest and most intense systems are overwhelmingly mid-latitude and not tropical. Intense convective events that also have high rainfall rates are pretty much exclusively over continents. Amazon's name Green Ocean is well deserved. And it is now pretty well established that the large and intense convective systems can grow from smaller events, and they form mesoscale convective systems. And a lot of what you just saw on the screen are what we would call mesoscale convective systems. Future event for if there's grad students interested in doing this, I think the next step in understanding and extrapolating to future climates is almost certainly if we were to composite the environmental conditions, assuming we have good enough data in the reanalysis, I think it would be an essential step before trying to anticipate, how these events would change in a future climate. And I do want to give a big thank you to this wonderful department and everybody in it for providing this old guy a very friendly and supportive environment so that I have actually been productive into my 80s. Who knew? I have to thank Chantal Liu. I'm glad he's here. Without Chantal creating user-friendly databases for a computer illiterate faculty member like me, I couldn't be doing things like this. A lot of the support comes from the precipitation science team of NASA, not all of it, but much of it. And I'm certainly hoping one more time to go back on the DC-8 in September. So with that, I'm going to close and hope there might be a few questions.
Okay, thank you, Ed. So questions, please. Raise your hand. Okay, let me start with a question. I come from a different field, but like much of your earlier work was from the TRIN satellite, and it's my understanding it's a radar satellite. And so the new work which you just presented today, what is this GPM core satellite, and can you sort of explain this a little bit to those not so familiar with it?
Yes, this is the GPM core satellite. I should have said that the GPM mission also includes many polar orbiting satellites with passive microwave on them. And the passive microwave is an extremely useful instrument. In fact, our group is using it in other work that Mani and Mani's work depends upon the passive microwave instruments, and James Russell and Peter Veal's work is also making good use of that, and Xiao's work as well. Yes, the global preset mission is a combination of the core satellite and the polar orbiting satellites with different equator crossing times.
Okay, but the data you used was from a radar satellite or not?
I don't think there are any other radar satellites. Well, of course, there is CloudSat. That's a very different radar frequency aimed at clouds, not at precipitation size particles. But yeah, Chantal and I felt that we had to concentrate on the radar data for so many different reasons. It turns out that one of the most important tools in working with radar data is to understand the vertical distribution of the reflectivity. I mean, of course, sometime in the future, we'd love to have Doppler in space, but that's another story that has not yet happened. Chantal may want to jump in with some answers here.
Okay, maybe Chantal is not listening right now. So I have a question by Haley. She's writing in the chat that do tropopause folds have any effect of the severity of storms in the mid-latitudes? So tropopause folds.
Tropopause folding. Let me find my chat. Oh, I see. Well, that's a good question. That's a good question. It really begs a related question, which is we pretty much know what the requirements for severe storms are. They require a certain sounding, typically with a lid, stable layer capping the warm, moist air, and then some mechanism for lifting the cap. Tropopause fold might be one of many synoptic scale features that would provide a mechanism for lifting the cap. Probably not essential, because when you look at the distribution of severe storms and tornadoes, they can occur in connection with intense cyclones and tropopause folding, but many of them do not. So it could be, but it's probably not essential.
Thank you.
Okay. Chantal?
Hey, Ed. Thank you for showing nice result we have. My comment, actually, I have a comment on the extreme rainfall. Many of those floodings are not really caused by the extremely rain rate, but more like a mediocre rain rate, like 20 millimeter per hour fall, but rain for a long time. And those events actually are not included in this analysis. But many of those are causing a significant flash of flooding, like a Boulder case or even for Colin's case.
That's absolutely right, of course. And people like Jim Smith and those who look at floods, everything that we've done depends on instantaneous view and not on duration. That is duration is a completely separate issue. And, other folks in our group, including Mani and Shishao, are looking at the time history of events, and typically the mesoscale convective system, as long as it's not moving too fast, are often very important precursors for that type of event.
There's a question by Steve Krüger.
Yeah, Steve. All of those heavy rain events over Northern Europe, that I think has surprised us quite a bit. Actually, I expected North America to have more of those events than Northern Europe, and I have not looked into the environmental conditions there. Maybe that's a great project for a student to look to, maybe as I suggested toward the end. I think it would be a great idea to take a set of these events over different regions, let's say the high plains of North America or central plains of North America, and contrast them with Northern Europe and see if there's any major differences. I think that'd be very interesting. And I think the frequency of those events over Northern Europe surprised me almost as much as their absence over the tropics.
Yeah, I thought you were going to allude to those after you mentioned the tropics, so that's why I asked.
Okay, do we have more comments or questions? If not, then I would thank you, Ed, one more time for this interesting talk. And I'm gonna close then this meeting, this seminar.
Thank you, Ed.
Yeah. Thank you all for having me. Yeah.
Thank you.
Thank
Ed.
you. Thank you.
Thank you.
See you, Chantal.
Good job, Ed.
Bye,
Nice,
Chantal.
nice clouds behind you.
Yep.
Someday somebody needs to tell me how to put clouds behind me instead of my kitchen. I've tried a few times to put a nice picture and I haven't figured it out yet.
Okay.
Yeah. See, I used to be a lot more productive when Chantal was down the hall. Yeah. Where are you, Jay?
Oh, I'm at home. I'm down in Sandy actually. So yeah, good job, Ed. I really enjoyed it.
Yeah, you've abandoned the cabin for the winter?
Well, I came down last weekend. Yeah, the walls were starting to close in on me just a touch, so I needed to sort of get a different horizon.
Yeah.
So, yeah. Well, anyway, good job. Appreciate it.
Okay.
Okay. Bye.
I think now I'll put this strange outfit back in the closet and
We'll see you later.
okay. See you all.
Okay, bye.
Bye, Ed. Thank you again.